Yes, hi guys, welcome again to another video of mine. This is Engineer AD and this is Mostly Academy on Physics 002, which is heat and thermodynamics. As we all know about heat and that thermodynamics is an aspect that is very, very wide and which is going to require lots of concentration and as well as determination, and also we also need to cover a lot of topics. Now, as usual, I will limit derivation and focus importantly, or more importantly, on the most important aspects and the most important formulas and most important resources that we need in order to clear all the doubt and how to solve numerical questions and so on and so forth. So in this video, we are starting from the first topic. There are a lot of topics under heat and thermodynamics, kinetic theory of that, which we call KTG. We also talk about thermal expansion, thermodynamic itself, and we also talk about heat and thermometry and so on and so forth. So all this will be discussed under the channel. Stay tuned, invite a friend, and don't forget to subscribe to this channel and share with a friend. So let's start with the topic of kinetic theory of gases. Now, about kinetic theory of gases, remember this is physics, we have to differentiate between the real and ideal gases. And about that, we are given what we call the postulate of KTG, of kinetic theory of gas. Now, there are 7 major postulates of kinetic theory of gas, which I think we might have studied in our early classes. The first and the most important one is that what we call the size of gases. We'll just list the 7 postulates. I'll take you through the explanation quickly. The second point we can write is also the elastic collision. The third point we can talk about the potential energy. So it's just for you guys to keep all these 7 postulates at the back of your mind. And as more you keep that in mind, it's very easy. The fourth one is talking about the random motion. The fifth point we can write is the instant connection. The instant connect. The 6 points we can write about effect on gravity, gravitational effect on gravity. And the seventh, which is the last postulate, is the famous PV is equals to nRT. So about this, what we are talking about is there are 7 major postulates of the kinetic theory of gases, which differentiate between the real gas and what ideal gas. About the size of a real gas now, I am focusing with respect to real gas. So every other property of real gas here will be the opposite for the ideal gas. So most of the theoretical and direct based question you can face in future is to give differences between the real and ideal gas, which is well taken from the postulate of kinetic theory of gas. Now, the size of real gases are said to be negligible because they are very, very small. So we say the size is negligible. For real gases, negligible. And for ideal gases, they are not negligible. Now, about collision, we have talked about that one. The size of the collision, you know, they contain what they collide from your chemistry knowledge with the wall of the containing vessels. And because they do that, we say the type of collision that occurs is between molecules and wall. Sometimes you can also have a situation of a collision that exists between molecules and molecules. So now the type of collision that you see in real gases are called what? Elastic collision. Whereas in ideal gases, we call it and what? Inelastic. You know, when they are stick together, that's many of our inelastic collision. We have also studied under the topic of momentum. So the next point of our action now is potential energy. Now we say the total sum of energy, the potential energy of a real gas is 0. That is the definition we give to it in the postulate. And for real gases, please. And the total sum of what energy is the total sum of energy of what? Of gases is the sum of what? The kinetic energy that is flowing through it. So we say the total sum of energy in real gases is the what? Is the summation. That is just a mathematical interpretation of what? All the number, what when you consider the number of molecules from 1 to what? To total number of molecules, which is equals to what? The sum of what? The kinetic what? Energy. Another important point is motion. The motion of a real gas is said to be random. And most importantly, you also call it what? Brownian motion, which is also very important, which I believe we have studied that one before in what? in early classes. So Brownian motion. Another important thing is talking about the connection. When we talk about the connection, there's also a kind of instant connection between real gases, which is not available in what? In ideal gases. Now, in real gases, students should keep it at the back of our mind. If we talk about real gases, there's also a kind of instant connect. So, and because of that, we say what? Their time of contact, the relationship we give to it, is time of contact of molecules. Time of contact of molecules is very, very less than relaxation time. So this is the interpretation. Relaxation, I think relaxation, the spelling there is wrong. Relaxation time. Then again, the next point, which is the sixth point about the postulate of kinetic theory of gas, is there is no what? Gravity has no effect on what? On real gases. And this is because we say what? Their density is what? Constant. So very important to keep in mind, density of real gases is constant. And the last one, which is also very important for you to keep at the back of your mind, is PV is equals to nRT. This is always going to be valid for real gases. Always valid. Valid always for what? For real gases. So these are the 7 postulates of the words of the KTG, which students need to keep in mind for theoretical form of questions you might face in future. Directly, size of gases, elastic collision, potential energy is 0, random motion, or we call it Brownian motion, instant connect, relaxation time is very, very what? Greater than what? The time of contact. Effect of gravity is 0 because density is constant, and PV is also nRT, which we call what? The ideal gas law is very, very valid always for what? For real what? Gases. So please keep that now for what? For ideal gases, you know what we talk about. Now another important point is that in terms of pressure, temperature, which is what we are still going to talk about in the later part of the checklist, and we are going to talk extensively on the relationship and how we come about all this stuff. So students should keep this in mind for future question or theoretical form of question about the postulate of kinetic theory of gas. We move to the next one. Good. About the next point now, we call what? The state of a gas. Now, the state of a gas from elementary class we might have studied is always represented in terms of what? The pressure, the volume, and its temperature. So we call that PVT. So these are the state of gas, which can change from one medium to another. So basically, we know when we have a closed container, let's take an instant of diagram for understanding's sake. And because I want this to be very, very fast because it's more of concept, calculations video sections are available on our other channel, which you can also try and subscribe. If you have the time to know about derivation, and most of all these things are also available. So back to base. Now we're talking about the most important thing. I want to talk about pressure. The state of a gas are always related in terms of its pressure, volume, and gas. In chemistry, we have studied quite a lot of all this. Now, let's say we have a closed container. Please let it be what known that when container is closed, the value of when container is closed, excuse me. Oh, wow. That is not a good idea. I'm trying to run away from the kind of what I call rough diagram. So let's say inside this now we have a change of process from one particular form to another, as I'm trying to do here, guys. Just illustration's sake. I know we have studied a lot in our early classes. So we have a process or a process change, or a change of process from one point to another. Permit my spelling. This is a closed container. Note that. So now when a container is closed, one thing we have learned in chemistry is what? The numbers of mole is what? Is constant. Numbers of mole is or are constant, as the case may be. So if that occurs, what we are talking about change of state is that the state of a gas, like I said, is always in terms of P, V, and T. So as we have studied, we say we take them as well. The first state is of P1, V1, and T1. Like I said, this is a closed container. So now because there is a process change, then it will what? The final pressure will be P2, V2, and T2. So from law of conservation of energy and what we have studied in our in our chemistry class, we have learned that from gas law, so we can say therefore from gas law now, which we say is valid for ideal gases, PV is equals to nRT. And if that is what's valid, from here we can try and make what nR subject of formula. So far we say number of mole is constant and R is what molar gas constant. We can say is equals to, we can say PV by T. So if PV by T is constant, according to what we have said, that means we can assume that therefore we can have different states like Boyle's law, Charles' law, changing the pressure, temperature, and stuff like that, which majorly you might have studied in your chemistry section. So now here, so because PV over T is constant, according to what we have said in change of state, so we can conclude that for P1, V1 by T1 is the same thing as P2, V2 by T2. So this, I believe you also have studied, and this is also always very valid, which we call our general gas equation or whatever you call it in your chemistry subject. So keep that in mind. A lot of processes can come, Boyle's law, Charles' law, and Gay-Lussac law. All these are actually subsets of what PV over T is constant, which can bring about when pressure is constant, when volume is constant, when temperature is constant. We have P1, V1 equals to P2, V2. We can have V1 over T1 equals to V2 over T2. All of these are subsets of what this particular change of state of gas, which is always in terms of pressure, volume, and temperature. I hope students understand that. We move to the next part of the slide. Yes, the next one still on kinetic theory of gas. This is mostly academic, and we are going to look into what we call the mixing of gas. Now, as we have talked about the state of gases, gases are being transformed in terms of their pressure, volume, and temperature. Now, let's take a situation whereby we have a closed system, as you can see in the diagram, shown here. From here, if we say this is at thermal equilibrium, what we mean by thermal equilibrium, when temperature is constant, let's say the pressure here is the P1, the second pressure is V1, then temperature is constant, we take it as T naught. So at the final state, because there's a change of process, we have P2, V2, and temperature remain constant. So now, so far temperature is constant, we call these, since temperature is constant, temperature is constant, this is known as thermal equilibrium. Now from that we can conclude thermal equilibrium, which I believe we might have studied. Now, the next thing is what here in this case now, we might actually look for the value of the final pressure when these two gases are mixed. That's this, they are mixed together. So now the final pressure, which I will denote now by P final. You can see we have mixed the two situations now together. So now if these are P1, V1, T naught and the P2, V2, T naught, it means together. So by our equation, we can say initially, and just let's write for understanding's sake, initially, we can say the first one from our gas equation, which we've derived the other time, we say initially is a P1 V1 over T naught must be equals to P2 V2 over T naught, because temperature is not changing, as you can see. And this must give us the final pressure, which is P final, which will be the addition of our first volume plus second volume divided by T naught. Temperature remains constant. So from here, derivation is very simple to do. You can say T naught gets cancelled out. So making PF subject formula, which is P final, the final pressure when gases are mixed, is always equals to, as you can see, have P1 V1 plus P2, sorry about this, it should be plus, because I'm mixing gas, the first phase plus the second phase. P1 V1 plus P2 V2 all over V1 plus V2. So it's another direct formula students can always keep at the back of their mind when you are looking for the final pressure of the gas. In case of a mixing of gases, the final pressure is always equals to P1 V1 plus P2 V2 divided by V1 plus V2. This can also happen in other cases, but in this case, we are talking about thermal equilibrium that exists. This also is going to be taught extensively under the topic of what we call the famous topic we call thermodynamics, where we talk about different types of changes, which we call, adiabatic change. We have isothermal, isochoric, and so on and so forth for now, isobaric and the rest, and what and another other thing. So for now, students should keep this in mind because we are going to be using this formula to solve a lot of numerical questions as we move forward under the topic of heat and thermodynamics. Next slide. Now, another important thing here is what we call the Darting's laws of partial pressure. Now, in the chemistry syllabus, we might have a study about Darting's law of what partial pressure. What the law is all about is talking about change in pressure at constant volume and temperature. So from what I've talked about mixing of gases, we can also use the idea to actually derive the formula we use in calculating the Darting's law of partial pressure. Now, early, like I said in early classes, we might have a situation, just a quick one because of time. Time is always not on our side. We can take a different situation and use that situation to explain different process. So let's say we have in this case, I just want to consider 3 pressures. Now, 3 different pressures, as you can see, at constant volume. Wow, the third one is not coming. So that is that. So we have this is at constant volume and constant temperature. If the volume is constant, so I'll take the volume to be V, as you can see. So the first one, we have the first pressure is P1. The temperature is also constant, I take as T. The second case is also P2T, and the third case is P3T, as you can see. So here, each of these is now forming something like this. For standing sake. And you have this. Sorry about my hand. Like I'm not going to scale. So we have each of them as what they've moved, and technically they are going to give us a final effect. So let's say the final effect on this is diagram not going to scale, like I said. So P final is the final pressure. The temperature remains constant and the volume becomes constant. So from what we have discussed not quite long from mixing of gas, we can now say, therefore, the numerical derivation of Darting's law of partial pressure can say the first state is P1, V is constant, then T is constant, plus P2, we have V is constant, then T is constant, is equals to the P final. You can see, okay, I also have the third one. So we also have plus P3, V is constant, temperature is constant. It must give us the P final with volume constant, temperature constant. So numerically, you can just solve this by saying all this gets cancelled out and all the V at a constant gets cancelled out. So we say the final pressure from here, final pressure here is now equals to the sum of individual pressure. And this is what you call what Darting's law of partial. So if you are doing numerical calculation about Darting's law of partial pressure, the total sum of individual pressure will give you the total pressure of a gas that is active. So this is the way and the methodology we use to calculate the Darting's law of partial pressure in numerical. And you can also be asked to state the law. It's just that the total pressure of a gas is always, at constant volume and temperature, the total volume of a gas, pressure of a gas, is equal to the sum of individual pressure of that gas. And this is the numerical interpretation to it. In this case, I have only considered 3 states. If it is more than 3 states, so it continues to grow till infinity. I hope students understand this. And this is the third one about the Darting's law of partial pressure. The next concept will be in the next slide, and let's see what that is. Wow, the modified form of gas law. Now, as we have studied, we have said the gas law generally is given by PV is equals to nRT, which we have studied. And this particular form always holds for container form. The molecule of a gas inside container, container form. So in the other way, we can say, okay, from what we know that numbers of moles from chemistry, a little bit of chemistry is needed, is given as mass of substance over molar mass. I hope students still remember this. Then in atmospheric form, we can also say, remember, density is equals to mass over volume. I hope students still remember that density is equals to mass over volume, and pressure is equals to H rho G. So now if I want to change that, I can just change this one from PV equals to nRT. I can write it as let's say P is equals to, so far, volume is equals to mass over density. I hope students remember that, like from your Hydrostatic, we've talked about a lot of the volume is equals to mass over density, which is also very, very valid. Now, from here, you can now say pressure is equals to, if I substitute, you can see volume is mass by density. I'm now going to have density we denote by rho. Then you have rho RT divided by M, which is the mass. So now this particular form of equation, this is valid, is called the atmospheric form of gas equation. Atmospheric form of gas equation. So students need to keep this in mind too, because it's very, very valid. And sometimes this is container form. And when it is in the atmosphere, this is the relationship we give to it, because some question directly can ask you the atmospheric form, which you need pressure and stuff like that. Directly you can apply any of this, which is what very correct. Now, in continuation to what we are talking about, we say gas equation is PV is equals to nRT, which we all know it's valid for an ideal gas. Now, in continuation, number of moles is mass over molar mass. So we can modify the equation by writing PV, I hope students are following, is equals to, since N is equals to numbers of moles, now number of moles is mass over what? Over molar mass. Over molar mass, which I will use capital letter M, and you can write as what? RT. I hope students are following. So the next one we need to understand here is that what? The mass of a substance. Mass of a substance is equals to mass of one molecule of a substance, one molecule, M dash or M prime is mass of one molecule of a substance multiplied by the what we call what? The total number of molecules. Then again, molar mass of a substance is equals to mass of one substance multiplied by its Avogadro's number, which I will write by N capital letter A. So substituting that here, we can continue by saying, if I substitute that, I'm going to have PV is equals to, now from here, mass of a substance is M dash multiplied by the total number of molecules over, this is also M dash multiplied by Avogadro's number, both multiplied by RT. From what we have studied, this and this get cancelled out. And if they get cancelled out, now you can see N over NA. N here numbers of what? Total numbers of molecules. NA is what? Avogadro's number. In chemistry, 6.02 times 10 to the power 23. These are constant, which will be given in front of any calculation. So you don't need to cram or memorize that. Now, in continuation to that, we can now say the modified form can be PV. Sorry about that. So in continuation, we say PV is equals to, now we have two constants N over NA. Now students should also note something. Now here we say it is equals to N, this N up here, KT. Now this question is, where do we have KT? Keep this in mind, very important. R divided by NA. Molar gas constant divided by NA, which is Avogadro's number, is given by K. K is called the Boltzmann constant. So Boltzmann constant, also numerical value will be given in your slide, which is also very important in calculation. So this particular form of equation in which we have derived, PV equals to NKT, is called the modified form of what? Of gases. So students need to keep it in mind. Also, in future, we are going to be needing all these formulas we are deriving in solving questions directly, which will not what? Because one thing is knowing the concept, one thing is what? Applying the formula. So most of us, when I use formula in classes, in my offline classes, most students just say, how do we come about the formula? This is the way we come about the formula, which is even very important than cramming the formula itself. So now the next point of our slide should be, fine. Now, barometric relation, glass tube and glass tube with mercury and air. Fine. Now, from we are going to apply our law of our Pascal principle in understanding of this. This is a very, very simple something. Now, from what we can see here, we have a vacuum, we have mercury. The knowledge is, if we fill this, the moment we invert this, whatever, the level of this thing we write to a certain height. So which is what we have now from here. Atmospheric pressure at sea level, please keep this in mind, is always given as a constant. In physics, is always given as 76 centimeters. That is atmospheric pressure at sea level, which is the same thing as that of mercury. So total atmospheric pressure, numerically, we say P atmospheric from Pascal principle, P equals to H rho G. Remember, so we have H, which is the height, then rho of mercury, that is density of mercury, multiplied by gravity. So the value of this numerical is always 1.01 times 10 raised to the power 5 Pascal. Keep that in mind. So generally what we are trying to say here is that to calculate the pressure. Now you can see the pressure of mercury gas, the pair of mercury gas is the same thing as what that of what atmospheric, which is always taken to be what 76. So it depends on the position of the glass tube, the way it is, if it is inverted, if it is straight horizontally inclined, and if it is what the other way. All these I'm going to talk about, but basically we should understand that the knowledge of this is what we are using here, and the P atmospheric here is always HOG. Now to get the value of H directly here, it's very simple to just substitute the value, and by that we can get the value of H. So talking about the relationship of atmospheric pressure and the height of container, the height when a barometric fluid, it's when the what you can say when it is being what insert. What we see initially is that what the barometric relation, which I think I still need to talk about for us to understand, is what we take pressure as a function of height. That is the way we want to relate that, as in pressure is a function of height. You know, we say pressure increases with increases depth and height. And that is a very good example. So the pressure, as this thing is rising, the pressure also tends to increase. So the direct relationship we say is that what the final pressure is equals to what the initial pressure at sea level, which I call 76. So it's exponentially related, e raised to power negative mgh by RT. So we talk about a particular formula now. If you remember, we can convert this particular m into what another thing. That is, if you want it in terms of what Boltzmann constant. So P naught, I say, is the pressure at sea level. And when we try to graph that, when we graph that, what we have, let me help you graph that because it's also very important. And we try to graph that. If we graph that, we are going to have something like this. We just shift this a little bit up. So we have something like an exponential function, which is what students should know. So we are graphing the pressure at the sea level against the height. So you can see that atmospheric pressure is what reducing, what is decreasing exponentially, decreasing what exponentially. So which I think we just need to understand. So the major thing I want you guys to keep in mind, exponentially. So the major thing I want you guys to keep in mind here is that what this particular relation is also very good for some of us that we are doing advanced physics, and we might actually need it to solve some question. Who knows? In near future. So now, for now, we are now going to talk about the different cases of our glass tube with mercury and air, because for elementary purpose, a lot of questions is what most students face, and what you see them saying is that they don't understand how they relate with relationship between glass tube and mercury in air. So it is very simple to understand that, but to get that particular stuff, we need to draw some diagram. Permit my diagram for you to understand. Let's say we have a glass tube. Like I said, permit my diagram that is filled with mercury. Just a quick derivation of how to apply all this, because it's very important for basic questions and fundamental questions we might have faced. Now, like I said, if this is the mercury inside this glass tube, I will write mercury as Hg. That's the symbol for mercury for those who don't know. Then this is the air. Then if here it is being trapped, as you can see, let's say the height of mercury here inside this container was 10 centimeters. And let's say initially, I'm just giving values from my head. The height of the air column is 30 centimeters. Anytime you see questions in form of words, you'll be the one that draw that. So this is the initial position of the mercury tube. Now, like I said, the atmospheric pressure is always taken to what? P atmospheric, I say it's always 76. So always keep that in mind. Atmospheric is always 76 centimeters. So if this particular thing was now, there are different cases. So let me take the first case. Now, if this thing was now inverted, this particular thing now was now inverted to form something like this. Diagram not done to scale, excuse me. So this thing is now forming something like this now. In this situation, as we can see, the mercury level has now come here. And because the mercury level has come there, still the same mercury level, remember? So we are now, this is the what? The vacuum now, which is the air. We are now to calculate the length of this. Now, in this time now, here, this is where the atmospheric pressure is coming. In this situation now, the atmospheric pressure is now coming from there to there. Now, remember that the atmospheric pressure, the length of mercury, this thing is given as 10, according to the question. So to get this now, remember atmospheric pressure may not be given, but it's a constant. It's always 76 centimeters. So the question can ask you to find the value of the length. So directly, my dear student, we can apply the knowledge of Boyle's law. And by Boyle's law, relationship of P1 V1 equals to what? P2 V2, because we take temperature to be constant. So in case of situation whereby mercury and air relation, which is mostly what you see in elementary level and basic level of calculations and numerical. This is the way you interpret it. So in this case now, because we say pressure is what? It's a function of height. In this relationship, we say the total pressure here is now 76 plus 10. You can see, my dear student, 76 plus 10, that is 86. That is the way we relate. Please note that. Not multiplied by, this is the length times the area. Area is not given. You can just take area to be A, which will be constant in 2 because it's the same 2. It's just what? Turned upside down. So by that, my dear student, we can just take that to be 30. Direct relationship is very easy to understand. So is now equals to, in this case now, the second table, you can see is upside down. So what we do is 76 minus 10. We subtract when it is being inverted. It will be 76 minus 10. That is 66 times V2. I hope students understand. The value of V2 is what you are going to get here. Numerically, you can do that. I'm not going to write answer divided by 66, which will give you a certain answer. And that is the right answer to that question. So another case in which you can also have is if this same thing is now being inverted, horizontal inversion, or horizontal, whatever you call it. In case of horizontal inversion, look at this, the same thing, this case 2 now. If it is like this, my dear student, it's also very easy to understand. The concept we follow in this situation is that you can see horizontal inversion. We say the value of what we are looking for, the length displaced by the vacuum, which is the length, still the same question. So, but now look at the direction of horizontal inversion. So the atmospheric pressure will come from it. So when it is being inverted horizontally, we take the P atmospheric to still be the same value. So directly we just say, using the same formula, P1 V1 equals to P2 V2 from Boyle's law. So we say that 86, the first one is 86, times the first, that is 30. In this case now, P atmospheric is the same thing as what? 76. You don't need to add to what? Any value of what? Of this thing. So because it is the same when we have horizontal inversion. Please keep that in mind. So it will be 76 times V2. So the rest is just for you to get V2, which you get the, what's the particular answer. So I hope students understand this. This is the methodology we use to solve this type of questions. And this is just based on fundamental and elementary level. For advanced level students, other ways in which we can have a seal tube, whereby it is sealed at front and back. We also use the same knowledge of this to break it down. We just look for the direction in which it has been displaced. All this has been done in our online full course program, which you can subscribe to if you want. So we move to the next one. The next point about this thing now, about KTG, should be, wow, molecular speed of gas. Molecular speed of gas. Now, about molecular speed of gas, for us to understand that, I need to draw a graph. And from that graph, it is just a graph that relates the number of molecules of gas with respect to what? The velocity. And according to Maxwell equation, we don't need to learn too much of concept. It's just for you to get how it is being done. Now, it is something like what? A symmetrical pattern. Let me see if I can see a symmetrical pattern to draw something. It's not all that straight, but let us just assume. So now to do this, my dear student, we are plotting a graph of numbers of molecules. Numbers of molecules against velocity. Velocity. Many a time, most people call it Maxwell velocity. So we want to look at the relationship. All these things are being done or carried out experimentally. That is the truth about it. So if we talk about that now, we are going to take an elemental position. That is a very, very small position. And that will need our knowledge of integration, as we have studied before under the basis of calculus. Like I do say, for you to know physics very well, you must start from what? Basis of calculus and vector before you start introduction to physics. It's very important. Now, let's take the first one. We take a very, very low part. We are considering the very, very low part, which I will take as this. So let's take velocity v, initial velocity v, the velocity of a molecule at a particular point of where the number of molecules is n. Then maybe we have an elemental shift. That's just a small shift. We move from v now to another point we call v plus dv. As usual, it is nothing so difficult to understand. At least there's an elemental shift in my velocity from one point to another. Then definitely there'll be there'll be a change in the number of molecules, which we call what? We call that what? dn now. That is the new change when I move from a particular velocity to that. So now this is what we are talking about. So the total number of molecules is given numerically and experimentally for as what? Integration of what? The function of f dv, taking the limit of, sorry guys, taking the limit from 0 to infinity, because we can also actually take different positions at this point. Like I said, f v dv, sorry guys, we are taking a function of velocity, changing velocity from 0 to infinity. So this is the general function notation we use for that to calculate the number of molecules of gases, but it is carried out experimentally. So now, if we continue to take that, we now take what we call the most probable what? Velocity, which is another important point we need to keep in mind, my dear student. The most probable velocity will be very close to the center, now, which we call VMP, most probable velocity. So the most probable velocity from experimental relationship is always given as square root of derivation. You may not need it for now, 2RT by m. I hope students know what all these parameters stand for: molar gas constant, temperature, and what? Molar mass. So please keep that in the back. So this is called most probable velocity of a gas. And at that point, what we call the most probable velocity of a gas, that particular point, we have the maximum number of molecules. So you can see why we need that. So at the most probable point, we have at maximum, just like saying at maximum from your math knowledge. So the what we call n is what? Maximum. Numbers of molecule is maximum. And at that particular point, this is the relationship. So at maximum, the most probable velocity is given as square root of 2RT by m, which is very important for all students to keep in mind. So the next point is what? We also consider the mean velocity. So if we say mean velocity, I hope students understand, which, let me use a broken line for understanding's sake, the mean velocity. So now at the mean velocity, I'll write that one as V mean. So to get that, the mean velocity of what? Of a molecule, of gas molecule, is just addition of all the velocity together, absolute value, because the direction of the direction of gas molecule can be in different, they are random. So why we are using absolute or modulo form is because we neglect negative values. Now, V1 plus V2, you continue adding to what? Let's say to Vn. N means what? To a particular number divided by the what? Numbers of molecules. So if we go by that, the V mean, which is also an important formula, it also is equals to square root of 8RT divided by pi, capital letter M. So it's another important formula students need to keep in mind. Like I do say, whenever you see me marking a formula, it is very important to keep it at the back of that. So the last one, which is the most important one, my dear student, is what we call the root mean square velocity. Let me change to a black. RMS. So the root mean square velocity is the general term, the general relation we use for what? For the speed, or for gas molecule. So this is the most important formula. In fact, in most advanced question in your 100 and 200 level, you have to calculate the root mean square velocity of gas molecule. And by that we take a symmetrical pattern also immediately after the mean of this. And at that particular point, we say this is the what we call the V root mean square value. So, and by that, we say the formula for that is the same thing as for you to understand how we come about it. It's just the same thing as squaring the mean velocity. So how do we get about the root mean square velocity of gas, which is, I said, the general relation we use? We just have to square individual velocity, just like what we did here. We are just squaring the value of what is here to, let's continue to Vn. I don't want to waste our time. Vn squared, n squared. We are now dividing it by what? It is a square root by n. So then the formula directly, which I said derivation is not important for now, but application is very, very important. So it's always equals to, and see, 3RT by what? By capital N. So this is what we need for us to keep at the back of our mind. So directly, my dear student, for the root mean square velocity, which is the general method or methodology we need to keep in mind, is what? 3RT divided by m, whereby the velocity at what the most probable velocity is 2RT by m, and what the mean velocity itself is what? 8RT divided by pi m. So guys, I implore you to keep these three formula for the velocity of gas molecule as they collide with each other inside the container. Like I said, they have infinite number of ways, and these are calculated experimentally, but the direct application and derivation of the formula will be using numericals, and that is why we talk about this. So my dear student, let's move into the next slide. And about the next slide, we have what we call the translational kinetic energy of the gas. Now, this is another very, very important aspect, which I think my dear students need to keep at the back of their mind. Now, we are going to consider, I'm trying to bring something that is going to make sense. Let's consider something. Wow, this is too big. I know the same. I think we can reduce that now. Now we have, let's just take a closed container as usual. Wow. So now we have a closed container, and let's just take, like I do say, let's take a gas of what? Of mass, or one molecule of a gas of mass, I'll just take it as m dash. So I'm talking about what? The mass of one molecule, just one molecule of a gas. That is what I'm taking into what? I want to talk about the translational kinetic energy that we have studied. Now, because we know inside a closed container, gases move randomly. We've talked about that. And because of their random movement, so they will start moving with different velocities. So let me just try to bring something that is also very important. My dear students, sorry about that. Now we say if gases are moving in different positions, let's say this move with velocity of v towards the x direction, another velocity here. So that's that. This is towards the y direction. And let's say another one is towards the what? Z direction. So I take the body is now moving with the velocity of v, mass of m dash, one molecule, mass of one molecule. So velocity can be in y direction. All these are simple things. X direction and what? Z direction. What I'm trying to tell you is that what molecule of gas moves randomly about their new position. So we can say the kinetic energy from what we have learned from work energy and power is half mv squared. So we take them one by one, because now we have half m dash vx squared plus half m dash vy squared. I hope students are following, plus half m dash vz squared or vz squared, anyhow you want to call it. So directly we can now say kinetic energy is now equals to the total kinetic energy. Like I said, the general relation we use for velocity of what is the root mean square velocity, which we talked about in the what in the last class. The root mean square velocity, remember, is square root of 3RT by capital letter what? I hope students are still following. So we say the total kinetic energy of one molecule, because I'm considering just one molecule, is given as a half m dash, then multiplied by v squared of the what? Root mean square. So which is the general relation we use. So keep in mind, general relation we use. So having said that, in continuation to them, my dear student, so we can now say the kinetic energy, therefore, the kinetic energy, all these are basic things. kinetic energy can now be said, right, by substituting the formula half m dash multiplied by, you can see, square root of, this is v squared, that is 3RT by capital letter M, all square. What happened, dear students? Square cancel the square root, and as square cancel the square root, what we are having here is the same thing as saying we have 1 by 2, or you say half, mass of one molecule of a gas times, you can see, this is 3RT by capital letter M. I'm still coming somewhere. Remember the definition I gave to capital letter M, molar mass of what? Of a substance is equals to mass of one molecule multiplied by its Avogadro's number, which we call Na. Always keep this in mind. I don't think it is too much for you to know that. So directly you can just say this is simple as saying by substituting that. I don't think this should give us any issues. So from there, we can say this is 3 over 2. This 3 here, square root is gone. That is 3 over 2. If I substitute where I see capital letter M as M times Na. I hope students are there. And remember, I'm going to have something like this. Maybe I should take it one by one. 3 over 2. This is 3 over 2. Then this is M dash, because M dash we get cancelled out. 3RT divided by, we can see capital letter M is M dash multiplied by Na. Remember this? The next point of action is what? M dash gets cancelled out. And if M dash gets cancelled out, we are left with the formula for kinetic energy of what? Of one molecule of a gas is now 3 over 2. There's no 3 here. Excuse me, guys. We have 3 over 2 R over NAT. Remember R over NA? What do we call R over NA? That is what? Boltzmann constant. Boltzmann constant is what? R divided by Na. So we can say this is simply as saying 3 over 2 kT. So this is the way we relate that, and this is the method we use. So we say the kinetic energy for one molecule of a gas, just one molecule of a gas, is given by 3 over 2 kT. So directly we can now say in continuation, therefore, maybe I should rule, therefore in continuation, generally we can give a general formula to that by saying, therefore, if we have total kinetic energy of gas molecule, total energy of gas molecule, or total kinetic energy can now be given if there are more than one. You know what it means? So if there are more than one, we can now say we need to, oh, wow. So if there are more than one, that means we are talking about the total number of molecules. So for total gas now, we now say 3 over 2. So 3 over 2 times N times K times T. So where N is talking about the numbers of the molecule. So this is the general formula we use. So 3 over 2 NKT. And remember, you can also remodify this one as by saying 3 over 2, because you remember that capital N is numbers of moles. And because of that, you can think in terms of the formula we call this is the same thing as saying N times what? nRT. So either you use it in this form or in this form. All these are very, very correct. And this is the formula we give to the total energy of gas molecule. So keep this in mind, either nRT, and you can also, another person can say this is simply as saying 3 over 2, nRT is same as PVT, because PV is equals to nRT. Anyhow you want to write it, it's always valid. Another person can say total energy of gas molecule is 3 over 2, nR is PV. You can say nRT is PV, 3 over 2 PV, so which is also valid. So these are things you just need to keep in mind. Many times I use this formula, most of them we just say, how is it 3 over 2? How did I come about all that? This is the way we come about that, using the knowledge of Boltzmann constant and the root mean square velocity of the gas. So this is the way we do this, and this is the method we use under the kinetic theory of gas. And I think we still have one more slide to go, I guess. So about the next slide, we have equipartition and degree of freedom. Degree of freedom. Now, degree of freedom majorly is shortened as DOF. Now, the degree of freedom. Now, we need to understand the concept about this. I'm going to illustrate for us to understand what we call degree of freedom of gas molecule. Now, gas molecule can actually undergo different kind of degree of freedom. As they collide with each other, they can move, the molecules about their main position can move translationally. We know the motion in them is erratic, it's random motion or random motion. So, but degree of movement, degree of freedom, when particular movement is having freedom or molecule is having freedom, they can actually move in in 3 different patterns. The first pattern of degree of freedom we have in molecule of gas is called the translational movement, translational degree of freedom. So degree of freedom can be translational. Another type of degree of freedom we can also have is the case of what? Rotational. They can rotate. After collision, molecules can just move and rotate about its main position. So the degree of freedom can be rotational. And the last one, which is out of the scope of your syllabus, I only want to talk about it, which is vibrational. That one depends on the energy level. More of that is taken at chemistry, in the course of chemistry in your A-level courses when you get to 300 level. Now, translational degree of freedom is just a situation whereby we say the degree of freedom for translational is taken for now. I don't want you to have issues, so I'll just give you values for you to understand. For every translational degree of freedom, it is what? It is taken to be 3. Now, for rotational degree of freedom for molecule of gas, students should keep in mind that it is in 2 ways. So we have linear rotational, whereby the degree of freedom is taken to be 2. And we have another case where we call the non-linear, and it's monoatomic gas and diatomic gas. You should know that non-linear, which we talk about, we take the degree of freedom to be 3. So translational degree of freedom is taken to be 3. Rotational degree of freedom is taken to be 2. So generally, we can just say, whereby vibration, like I say for now, we can just take it as X because it depends on the energy level, which most of these things is going to be discussed under your topic of or the topic of chemistry in A level, talking about energy levels and that. This is actually at the above the scope of syllabus, and that is why I'm not going to talk about it. Not that it is difficult to derive, nothing is there, but for understanding's sake. Now, what do we call equipartition of what? Of degree of freedom. Now we are just talking about equipartition simply means the energy in different degree of freedom. Energy in, let me just say, in each degree of freedom. At a particular degree of freedom, there is a particular energy on that particular gas substance. So the energy at each degree of freedom is called equipartition of gas molecule. And generally, the formula for equipartition, which is energy at each degree of freedom, is given as half kT, whereby K is what? The Boltzmann constant. So from that, we can just say if it is a translational, then therefore the total energy at that particular point, if it's translational, it should just be what the energy it will now be equals to, from what we've talked about, that is 3/2 kT. That is for translational. So if it is a rotational can be in 2 cases. Let's change. If it is rotational can be rotational linear and rotational non-linear. For CO2, you need to know the structure of your gas, and that is what lets you know if it is linear or non-linear. Now, about rotational degree of freedom, we say the total energy for linear. You can see now we can see now what we are talking about. This is that is 3 plus 2. 3 plus 2 should be 5/2. Now this is already 3. That's 5/2 kT. And this one is 3 for non-linear is this is for linear rotation. And the last one is the non-linear rotational. Let's use a black. So it will be, what we do is we just add that particular value to initial value. So non-linear, the total energy will be equals to, you can see 3, then we have 3 plus 3, that is 6/2. 3 plus 3, that's 6/2. 6/2 kT, and 6/2 kT is same thing as saying 3 kT. So this is the general way we translate degree of freedom with respect to what? Whenever degree of freedom is given in question. So be careful to know this is the general formula, 1/2 kT. So total energy is always 3/2 kT. That's the total energy for translational. So if it is this one, we have 3 plus 2, that is 5. So if it is the other one, 3 plus 3, that is 6/2 kT, which is 3 kT. So the general form, which I think is important, because this is where I will stop, or I think I have one more slide. So the general form in terms of degree of freedom or general formula can be given as the total energy of gas molecule in terms of degree of freedom is F/2 kT. K is Boltzmann constant. So total energy can also be written as U is equals to F/2 K, which is the same thing as what? NR. We've talked about that, nRT. So this formula you can keep back at the back of your mind. Like I say, nRT is the same as PV. So this is called the total energy of the gas, total internal energy of the gas, total internal energy of the gas. So this is the formula which you see me using around one or the other in terms of degree of freedom, F/2 nRT, 3/2, 5/2, and so on and so forth. So guys, this is the way we illustrate that. And I think we have one more slide to go here. Okay, fine. Mixing of gases at different temperature. Now, if we mix gases at different temperature, let's just consider it's just the case of mixing for understanding's sake and for us to understand what we mean by mixing. So maybe we have N gases. Let's consider N gases. N gases means we have numbers of gases that has a different number of moles, that has different number of degree of freedom, and that has different temperature. So I'm considering 3 facts: moles, because of experience. We have degree of freedoms, DOF, and we have temperature. So we have N gases having number of moles. Let's just take N1, N2, N3 to what? Nn. Degree of freedom, we take it as F1, F2, F3 to Fn. So temperature also, we say T1, T2, just considering different temperature to Fn, say Tn. So directly we can say at equilibrium temperature from what we've studied. So for equilibrium temperature to set in, so what we do now, that means temperature is constant, that's what we are saying. So we add all this one, we can say degree of freedom of the first one, multiplied by number of mole of the first one, multiplied by temperature of the first one. We add it to degree of freedom of the second one, number of mole of the second one, temperature of the second one, third. Then we continue in this manner. Third one, number of molecules of the third one, temperature of the third one. We divide all that because we are looking for the equilibrium temperature. That is our T1 plus, we have F1, N1 plus temperature is constant, F2, N2 plus F3, N3. Now it continues to go towards Fn, Nn, and Tn. So the same thing is applicable here, Fn and what N, this is Nn. So now what I'm just saying is a very, very simple illustration when you are mixing gases at different temperature, more or less like what I have derived in the other stuff. Remember that it's just adding, if you are given values for the degree of freedom, number of moles and temperature, no matter the numbers of gases you have, add them together to get the temperature, equilibrium temperature of all the gases that has been mixed. So, and don't always remember to what they call your formula of P1V1 over T1, right? Plus P2 PV2 over T2. You know that we give you what P1, that is our P final, bracket V1 plus V2. So this is also very, very important. So guys, this is where we stop. See you guys soon in my future video. So don't forget to subscribe and like the channel. Numerical solution will be available later. Thank you and remain blessed. Bye for now.